now the exams have been rescheduled. So just now become serious here. It's not a joke to prepare online, and even we are doing hard work. So please pay attention. At least you guys should pay some attention from now. Okay. Nevertheless, we'll start with our lecture number 4. So this is the table of content for today's lecture. This lecture is also important, in which we'll study about material media, the types of material media, and I'll teach you about conductors and semiconductors and dielectrics. And then we'll study electric polarization in all, like polarization in conductors, in semiconductors, and in dielectrics too. And at last, we'll see some boundary conditions which we will apply in our problems while solving the questions of polarization. And we'll do some questions of previous year papers also. So, material media. So, you guys already know what is a material and what is a material media. Material means any substance. So, on the aspects of magnetic and magnetic field and the response to magnetization, the material media can be classified as conductors and semiconductors, which is based on the electrical properties of them, and then dielectrics, and then magnetic materials, which is based on magnetic properties of them, magnetic materials. So we'll start with the conductors and semiconductors. So the definitions, you already know that what are the conductors and what are the semiconductors. So basically conductors are based upon the property of conduction. That means they have the free electrons, and the current can pass to them due to the drift of those free electrons in the material. So in the conductors, there is always average velocity of the charges regarding to the applied electric field. And what about semiconductors? So semiconductors are those who are not insulators nor conductors, but having the properties in between. So here is a schematic diagram of an atom in which we can probe the polarization as the nucleus, and around the nucleus there is electron cloud. Electron cloud means whole the density of electrons is mid between this region. Okay, so let me select some pen or pointer. Yeah, so the electrons are in mid between this space. In this space there may be some free electrons, and there may be some valence electrons, and there may be some bound electrons. So you guys know the difference between free electrons and bound electrons. Free electrons are those which are free to move and which are always available to make a bond or to do a chemical reaction, and bound electrons are those which are bounded to the nucleus or to further charges, to some charges with some static force, with some strong forces. Okay, so in semiconductors, conduction occurs not only by electrons but also by holes. You know these things. What are the holes? The holes are the vacancies created by the detachment of electrons. If we want to detach an electron from an electron cloud, so we have to put some external effort to do so, and after the detachment of electron there is a vacancy created, and that vacancy is a hole. Now the vacancy is positively charged, so the holes are always positively charged. So we have two types of charges in a semiconductor. Electrons means negatively charged particles, and holes means positively charged particles. So whether we will talk about semiconductors, we will consider two types of charges, but will not do the same in conductors, insulators, and dielectrics. So the conduction current, the formula for conduction current or current density, that is from Ohm's law at any point. So that is Jc equals to sigma E, where J is the current density and sigma is basically, you know that from Ohm's law we talk about the resistivity and conductivity. So this sigma is the conductivity and E is the electric field applied. So this is the conduction current density. So we'll talk about this sigma. Sigma is basically conductivity, and for the conductors, this sigma is mu e n e e. E is the charge and E is the number of charges, and mu will define it later. This is basically the density. So for mu e, we are talking about the electrons, and this formula for semiconductors in which this mu h is all about the hole. So for sigma for semiconductor, sigma equals to mu h nh e plus mu e n e e. Okay, this mu is mobility. Mobility means the average velocity per unit density, or we can say the movement of any charge is a mobility. And you know nh is density of holes or electrons. So this was the Ohm's law. We know that from Ohm's law, Jc equals to sigma E. This formula is well known from the previous classes too. And we know the relation between voltage and electric field is V equals to EL. So what is E from here? E is V over L, and we are putting this instead of this E. So we are getting sigma V over L. The current is basically the current density also has one more formula, that is current upon unit area, current density. So I is equals to now Jc over E. So we know the value of Jc, we have derived, that is sigma V over L. So we are putting this, and from here we are getting this V as V equals to IL over sigma A. You know that V equals to IR is your Ohm's law. So if we are comparing these both, this one and this one, we are getting this I is same. That means R is L over sigma A. This R is the resistance according to the Ohm's law. So from here again, we can get what is sigma. So basically the sigma will be L over RA. So this is quite easy, L over RA. Okay, so if we talk about the conductor in a static electric field, suppose we have put any conductor in the constant or static electric field. Static means constant. The static electric field means the value of electric field is constant everywhere at every point. So the conductor in a static electric field, if it is put, then the polarization takes place. How the phenomena is taking place, that some positive charges are accumulated on one side, whereas some negative charges are accumulated at another side, and hence the conductor is now polarized. One side there is all positive charge and one side there is all negative charge. So this phenomena happens where the conductor, we put a conductor in a static electric field. So we'll take an example. We'll put a plain conducting slab in a uniform electric field. So let's see what happens. So this is your electric field. This electric field in this direction, from here to here, from south to north direction, or we can say in Z direction. And we are putting a conducting slab. This is a slab. Okay, having the thickness, or we can say the width D. So if we are considering this surface situated at Z equals to 0, so this surface will be situated at Z equals to D, obviously. So what happens if we are putting a conducting slab in a uniform electric field, then the charges in that slab start accumulating in opposite directions and they will make a layer. How does this is happening? Like all the negative charges are accumulating on this side, on the north side, and all the positive charges are accumulating on the south side. So if we are considering this as a surface, and this as another surface, like this as a surface and this as another surface, then what we are getting for this surface, that is rho s, which will be epsilon naught E naught, and rho s will be epsilon naught E naught. For this it will be minus, and for this it will be plus. So see here again, if all positive charges are accumulated, then rho s naught we will consider, and all negative charges are accumulated here, then this negative minus minus rho s naught we are getting. So, okay, this is the same phenomena. And what is the important thing? The important thing is that we should always keep in mind the electric field inside a conductor is always zero. So there is no electric field inside the conductor, but there is always some surface charges, and that is why there is always some surface charge current. But inside electric field will be again zero, whether it is polarized or non-polarized. So this is the important thing. But outside, the electric field will change accordingly. How we can conclude that electric field, we can calculate that electric field, I'll tell you in this lecture only. So all the positive charges are now accumulated here, and due to these charges, if we are putting some surface, so that surface will be negatively charged because the positive charge will induce the opposite charge in sign, and the same phenomena will take place on this side. So if here is some on this surface or in the region between these two, plus and minus, if an electric field is generating, and we are considering that electric field as E naught. Okay, and that electric field will be quite different to the electric field which we are applying initially. Okay, this is that the conventional electric field, and some electric field will generate in mid between these plates, and some electric field will generate in mid between these plates too. So, what type of formula we will see? Am I audible? Hello, hello, hello. Can you hear me, guys?
Yes, ma'am.
Okay, okay. I thought I was disconnected. Okay. So, yeah. Okay. So this formula, these two formulas we will consider, and how we will make use of them, I will tell you. Okay. So we have talked about semiconductors again, then conductors, then we are coming on dielectrics. We are coming on dielectrics. So what are dielectrics? Dielectrics are not conductors. They are insulators, but when they get polarized, then they can behave as conductors. In property, they are insulators. So basically, dielectrics are based upon the property of polarization. Okay, which means some electric dipoles are created when polarization takes place, and those electric dipoles will be created within the material. Okay, whatever the material it is. So how does the electronic polarization? Electronic polarization means bound electrons are displaced to form a dipole. So how this phenomena will take place? Just see here. This is any atom, and we are putting this atom in the electric field. So what this atom will do, the volume density of this atom will be detached into two parts, and a cloud will form. One cloud will be all positively charged, and secondly will be a negatively charged, and they will create some infinitesimal distance between them. So this is that distance d, this is the positive charge and this is the negative charge. So this system is a dipole, and this will have the dipole moment P equals to QD. So this is how a dielectric can be polarized. So what are the effects if we are polarizing some dipole, or we are generating a dipole in a dielectric? So orientational polarization and ionic polarization, we will study these. So orientational, what is orientational polarization? The orientational polarization is already existing dipoles are acted upon by a torque. There were some dipoles already in those materials, and when we do polarize that material, when we apply some electric field, then those dipoles got excited and want to align in the direction of the conventional electric field. So when they will try to align themselves, then torque will be generated. So what will be that torque? Do you remember the formula we have studied in our last lecture about torque? The torque tau was P cross E. That means PE sine theta. What was that P? P was the dipole moment, and the dipole moment is QD. So the torque will be QED sine theta. Okay, and obviously here we are denoting this torque as T. So whenever the sine theta comes, we'll put a cross. So QD cross E, that QD is becoming P, so that is P cross E. And if we'll talk about ionic polarization, that means separation of positive and negative ions in molecules. Okay, we are not talking about charges. Here we are talking about ions. So the phenomena of polarization results in a polarization charge in material which produces a secondary electric field. The same phenomena was generated in the conductors too, but here it is dominating. The secondary electric field will dominate and it will have its specific formula too. So we have some applied electric field EA, we are applying at this atom, this one atom. So what will be the total electric field? The total electric field will possess the electric field applied plus the secondary electric field generated. So the dielectric is now polarized. And due to the polarization, we know that due to the polarization in dielectric, there is some polarization charge which generates. And that is why some secondary field also generates. So this secondary field will again put its effort on that atom. So the atom will possess the total electric field this type. So this is the whole phenomena which is taking place in the dielectrics. Let's take the same example which we have taken in the conductors. There is a plain dielectric slab in a uniform electric field. That was plain conducting slab. And now this is a plain dielectric slab. So this is the slab having some dielectrics, and we know that dielectrics have its internal electric field too. And when we have applied some electric field, then this is the EA. So dielectric will allow to electric field inside also. The conductors never allow, but the dielectrics allow the electric field to go through. The dielectric has the thickness d. If we are considering this surface on z equals to 0, then this surface will be on z equals to d. The same phenomena will take place. This surface is negatively charged and this surface is positively charged. Due to this dielectric, there will be some tiny dipoles which will generated inside the material. So these are those tiny dipoles. These tiny dipoles, whether they are not aligned, if they are not aligned in the same direction, this electric field will uh, make a effort will do a work to align them in the same direction. So if all the dipoles are now aligned, you can see in this image, all the dipoles are aligned, all the positive charges are upside and all the negative charges are downside. So we can conclude that this is happening. What is this? All the positive charges from on this side and all the negative charges on this side. Now, what you guys can see, you can see that the direction of electric field is now changed, because we know that the direction of electric field is always from positive to negative. So now the electrical direction will be this one. What is this? This is secondary electric field. Okay, we have applied some electric field which is generating some secondary electric field. So now the total electric field for a dielectric will be ea plus es. I think now it is easy to understand for you guys by observing these pictures. Okay, so what effects takes place when we are varying the time, when we are varying the oscillating current, and when we are varying the direction of electric field. So there are some images. Let me try to make you understand, guys, that if we are applying some electric field in this direction, suppose this is x direction or this is y direction. Okay, and this is your dielectric. Omega t is equals to 0. We are not varying this time, this omega t is 0. So what type of phenomena is taking place? The phenomena is taking place like all the positive charges are upside and all the negative charges are down towards it. The original phenomena we have studied about we have studied in the example of the slab. Now, what we are changing? We are changing this. Now, omega t is equals to pi by 4. That means we are varying the input wave. Okay. So, if omega t is equals to pi by 4, then what phenomena you guys can see? You can see that a number of positive charges or number of negative charges, you can see those are reduced. Here was three charges in each electron cloud. Here there are two charges only on each electric cloud. This is only a schematic representation. I am not saying that the number of charges are fixed. Number of charges will obviously more than 1,000, 10,000, or maybe lakhs, not 2 to 3, but this is only just easy example to understand. So the number of charges will reduced while omega t is equals to pi by 4. Next, if we are again changing this and we are putting omega t equals to pi by 2, now what will happen? All the charges are vanish. No positive charge, no negative charge. That means there is no free charge in the dielectric. What does it mean omega t equals to pi by 2? Pi by 2 means the phase is changed. If the input wave phase is changed, no polarization will take place. Okay, these are some important results. So listen me carefully. Okay, all these images and all this description in your J.D. Jackson book and in your book of Electrodynamics, Landau Lifshitz. Those are two scientists, good scientists, which were working in the electrodynamics field. So these are some good results. Now, what I am doing, I am now changing the direction of applied electric field. Now it is in this direction, downward means negative y-axis. So obviously one phenomena will occur, that is the negative charges will come upside and the positive charges will go down to the downside, okay, to this up. So if we have changed omega t up to 3 pi by 4, then obviously charges will be reduced again. And if we are doing the phase the same the previously was, that is omega t equals to pi, then again some new charges will generate, and so on. You can see with the rest of the diagrams, and you can understand this formula easily. That means the polarization current or the polarization in any dielectric will be according to the time varying case. Means the input wave will be considered, the direction of electric field will be considered, the time we are applying that also will be considered, and so on. So here is a formula. This is the electric dipole moment per unit volume, and the formula for electric dipole moment per unit volume is P equals to epsilon naught chi e e. What is this chi e? This is chi, and I am saying it as chi. I will write it as this one, chi. So this is chi. What is chi e? Electric susceptibility of the material. Okay, so for the field of infinite plane current sheet, like in the x direction, we can put it as epsilon naught chi e naught cos omega t. Okay, so if we are considering any example like two plates having charges q1 and minus q1 are separated by some infinitesimal distance delta, having the thickness delta y and the width delta z. So the total dipole moment will be according to this formula. According to this formula, what it will be? It will be px delta del y del z. Then just put the value of px. So if we are considering this whole is as q1, then we are getting q1 delta. So I will be dq1 over dt, and this is your current in this case. So these are some specific results. This is important example. This type of question was in TIFR paper. Okay, you can see from there. So this when we have to calculate the current density. What is the current density? Current upon unit area. So area is delta y delta z. We know the value of IPX. Just put that. Just we are putting minus epsilon naught chi e naught omega sine omega t. So this is we can consider as the sine omega t is the derivative of cos omega t now. So I can write this equation as this one also. So what is this? This is the value of your px again, and thus we are getting jpx equals to delta px over del t. This is the important result. Put a star. Remember this result. Keep in mind all the time. Okay. So now, what will be the effect of polarization on the Maxwell's equations? If you guys know now, there are four Maxwell's equations. We will also study those Maxwell equations later on. There will be some separate lectures because the topic of Maxwell equation is quite lengthy. So for the general knowledge, you know that there are four Maxwell equations. Okay, so for a free space, we can write them as one Maxwell equation using the Gauss law. We have written that D equals to epsilon naught E. You know this thing. So if I am doing one time derivative of this D, so delta dot D is used to be rho. Okay, from Maxwell equation, it is used to be rho. And we know that D equals to epsilon naught E from Gauss law. So I'm putting this one. And the second equation, another equation is from Maxwell equation is del cross H equals to J plus del D over del T. If you guys can't remember these Maxwell equations, I'll tell you some tricks also in my upcoming lectures so that you can make them easily remember. Okay, so del cross H will be J plus, and just put that value of D here. For dielectrics, del dot epsilon naught E is rho plus rho P. Rho P is due to polarization. Okay. So in the dielectric, there are two electric fields. Na? applied electric field and secondary electric field. And due to that secondary electric field, there are some tiny dipoles generated, and the dipole moment of those dipole, if we are doing some divergence, one time divergence of any dipole, any conventional dipole, then we are getting this rho p. So basically, this rho in the dielectric only is equal to minus divergence of P, minus divergence of P. This is only for the dielectric. So I can write this as this one, put these values in the Maxwell's equations. And finally, we are getting this type of result. Del cross H equals to J plus del D over del T. This is the important result. J plus del D over del T, where for the dielectrics, D is epsilon naught E plus P. So there are many formula in the electrostate, and if you want to solve more and more questions, so please guys make your own short notes where all the formulas will be written of electrostate, and frequently you have to learn them frequently. Just watch those formulas, read once in a day, and then you will solve the questions, and I'm sure you will be able to solve all the questions of electrostate. Why this electrodynamics is hard? Because there are more than enough formula we have to use in our questions. So make a strategy to learn them. Okay, so we have this D equals to epsilon naught E plus P. We know for the dielectric, this P is this one. So we are getting this, and this 1 plus chi A is epsilon R. What is this epsilon R? Epsilon R is your relative permittivity, and this is used to be equal to epsilon E. Epsilon R and epsilon vary with the material. Please keep in mind, in question, the value of epsilon r or epsilon they will give in your exam, but this epsilon naught is constant, having the value of 8.85 into 10 to the power minus 12. You know the numeric value. Okay, so as an example, let's consider some dielectric slab having the permittivity epsilon, and there is an electric field in the z direction. Due to this, the polarization is taking place. We know that inside the material there are two charges. So for plus rho, you guys remember the Gauss law for a sheet, Gauss law for a plane. Okay, so this formula is from Gauss law for a plane. So for the this side of plane, for this positive side of plane, there is electric field rho s over 2 epsilon Az, plus for this negative side of plane, there will be E of this one. So this minus and this minus. Why this minus? Because one is in this direction, okay, and the another one is in this direction, so the directions will also change. So we are getting this electric field as rho s Az over epsilon. Okay, so what is this D? D is epsilon E. So we are getting finally D equals to rho s Az. Az is your unit vector direction, not a specific quantity. Okay, we'll talk about some types of dielectrics. So there are two types, isotropic dielectrics and anisotropic dielectrics. The only difference between the both is in isotropic dielectric, D is parallel to electric field. That means displacement vector is always parallel to the electric field vector. And in anisotropic dielectric, D is not parallel to E. Okay. So if we are considering any isotropic dielectric, then this D and E will possess the same direction. You can see in this diagram. So if D is parallel to E, then dx will be equal to epsilon ex, dy will be equal to epsilon ey, dz will be equal to epsilon dz. Whatever the direction we'll consider both in the same direction. So finally D will be equal to epsilon E. But in anisotropic dielectrics, as D and E are not parallel, so only for certain directions E and D will be parallel. We will consider those cases will be also given in your question, and those specific polarizations are also known as characteristics polarization. Those polarizations are only happens in your anisotropic dielectrics. So for any anisotropic dielectric like this E and D having some angle theta, they are not parallel to each other. So what we will do, we will make a matrix. To solve these types of questions, the simplicity for simplicity, we'll make a matrix like this, and we can then solve the question 2. Okay, these are some examples of your daily life that can you see the phenomena of polarization in your daily life too? Yes, we can see. We see that lightning in the season of rain, the lightning from the cloud, the striking of electricity from sky to the ground, and sometimes that electric field is so strong that it can destroy many things. So, how that lightning is taking place? That is due to polarization of cloud. Have you ever studied about the polarization of a cloud? I think yes, you have studied in your 12th standard, but now we will study it in a vast way. This example is from the book of Griffiths. Okay, you can also see in that book also. I have shared on our WhatsApp group. So from there you can download and read this phenomena too. So let me tell you what is happening, how the polarization of a cloud is taking place. Clouds are basically made of the water droplets, the colloidal particles, some ice crystals, some ions, and so on. Some particles of sand and dust. So uh, the clouds have different types of ions. The clouds have different types of metals or molecules, and on all those some ions are presented. So basically when two clouds come together and strike to each other, there will be a strong friction between the molecules or the ions, and some charges are generated. Okay, some ions got free and they induce some charges. So the water droplets or the ice crystals or those colloidal particles also get charged, and some droplets are now positive charge, like some droplets will be positively charged due to the friction and the induction of charge, and some droplets will be negatively charged. Okay, some droplets will be negatively charged. Now, there will be a phenomena of polarization you guys can see here. The positive charge cloud will be one side and the negative charge cloud will be another side. Now, when the cloud is got dense and it starts raining and two clouds strike, polarization is happening in the cloud, and that is why the inside the cloud an electric field is generating. That you guys know that that is your secondary electric field. That electric field is so strong that it again coming, it is accumulating and it is coming to the earth or to the ground. Now, how electricity is reaching to the ground, how lightning is striking. You guys can see that this cloud is now polarized. This is your positive charge accumulated on one side of cloud and negative charge accumulated on another side of cloud. And now there is air in between these things. Okay, air. And do you guys know that the air have many types of ions and okay, uh, the air has many types of ions and basically air is a conductor. You guys know this thing, na? So the air between this cloud and the ground, this air between this cloud and the ground will do the work of charge carrier. The air is now charge carrier. The air gets ionized and that air conveys this negative charge to a tree or a ground as inducing of positive charge. Like positive charge is accumulated on the ground, positive charge is accumulated on this tree. And now this electric field is here only. I have told you that there is a secondary electric field in between this cloud. So the electric field wants to come from here to
Ma'am,
here, and as yes,
ma'am, your voice is breaking.
my voice is breaking. Okay, is it clear now? Is it
Yes,
clear
ma'am.
now or yes? Okay, it is clear. Okay, so when this there is secondary electric field. Okay, this
Yes.
okay. So we are moving ahead from this one. Okay, so we were talking about the lightning strikes, that how the clouds have been polarized and how they can polarize the trees and the ground as well, due to the air, because the air is also ionized. So the clouds can generate the electric field, and due to that electric field is reaching from here to here, and due to this a type of damage can be created on the ground. So can we make any way to less that damage? Yes. So scientists have prepared some lightning rods, and those rods have been grounded through a copper wire. So how it is happening in big cities? There are some high heights buildings having more than 100 to 200 grounds and floors. So they put a a rod of mixed metal on the top of that building, and when the lightning strikes, when the clouds are polarized and the light want to come to the ground, this point there used to be a sharp point of this road, and that point uh, attracts all those charges. So all those charges will fall onto that tip, and that tip is connected to a copper wire. That wire is grounded. Okay, so all the current through this wire will get inside this ground, and thus we can save this building from the damage when lightning strikes. So this is the daily use of your polarization phenomena. So we were talking about those formation of dipoles in the dielectrics now. So those tiny dipoles, also the polarized one. So they have the polarization. That polarization, the formula of that polarization is P equals to summation Pi over B, where this Pi is dipole moment. Obviously, in dielectric materials, there used to be two types of charge, bound charge density. that is sigma b and rho b. Sigma b is p dot n, and this rho b is minus del dot p, or divergence of this p. What is this p? This p is polarization. We'll talk about some boundary condition. So for the polarization phenomena, we will use these boundary conditions. So please learn these boundary conditions. Keep in mind them always, because in June 2019, there was a question in CSIR NET that amongst these options, which one is not a boundary condition for any polarized material. So there were four options in which three were right, but one boundary condition was wrong. So these are the boundary conditions. Okay. So a short discuss about the capacitors. You guys know what are the capacitors. So capacitors are those devices for store electrical energy, and in a controlled manner they can release that electrical energy too. And obviously capacitors having two conductors, having charge plus q and minus q, and separated usually by a non-conducting material or an insulator. We have studied about the types of dielectrics too. We can insert the dielectrics in between those plates too. Symbol of this capacitor is this one, and it takes work which is then stored as potential energy in electric field, and that is set up between the two plates to place charges on conducting plates of capacitor. So the electric field, the work, the capacitance, all these things we'll study one by one. So there are two types of configuration of a capacitor. In a general capacitor, we see this type of configuration. Two plates are separated by a small distance d, having one plate positive charge and another is negative charge. There used to be a potential difference between these two plates, and these two plates are connected with the wires. These two plates can possess different areas or the same areas, and this type of configuration is a capacitor. So they in fact can be any two conducting objects, as told you. For conductor A, there may be another type of conductor, and conductor B may be another type of conductor. So these plates may possess different area, or maybe same area, or may possess different material. So, what is the capacitance? When we are talking about capacitor, we'll also talk about the capacitance. So, the capacitance is defined to be the ratio of amount of charge that is on the capacitor. So, this C is equal to Q over V. V is potential difference, Q is charge. And the unit of that capacitance is farad. So 1 farad equals to 1 coulomb per 1 volt. But why we are considering farad and why we are not taking as coulomb per volt? The unit farad is usually a big unit. If we'll talk about 1 farad, then we are talking a monster type of capacitor. But we can't do this, because in electric devices we have to use as small as we can. So the capacitor should be small. So to do this, we'll use this farad unit in very small units like microfarad and nanofarad, etc. So while we are calculating some capacitance, like let the conducting plates have area A and separated by a distance d. So what formula we will use? For electric field between them, we will use sigma or epsilon, because sigma or epsilon is from Gauss law. You know these things. There are two plates, so sigma or epsilon naught plus sigma or epsilon naught, 2 epsilon naught plus sigma or 2 epsilon naught is now sigma or epsilon naught. So this will become Q over epsilon naught A, because this sigma is, what is the sigma? The sigma is surface charge density, that is Q over A. So the electric field we can calculate by this formula, and the potential difference is usually electric field into the length. So this is QD over A epsilon naught. And putting this all together, we have for the capacitance, this capacitance is used to be Q over VAB now. So we are putting just the value of this potential difference and we are getting epsilon naught A over D. We'll use this formula while calculating the capacitance for a system of capacitors. So the capacitance is only dependent upon geometry of the capacitor, not the potential difference and not the dielectric material and so on, just geometry of that capacitor. So, okay, I was telling you that 1 farad is a big unit. Why? If we have a 1 farad parallel plate capacitor having a plate separation of 1 millimeter. So what is the area of plates? Let's calculate. We know that C equals to epsilon naught A over D. And we are rearranging this A. So this A is equal to CD over epsilon. So CD over epsilon naught, we are putting the value of C, we are putting the value of D, and we are putting the value of epsilon. So we are getting 1.1 into 10 to the power 8 meters square. That means the plate of area is more than 10 kilometer. Okay, so is it possible to make a capacitance having this big area? More than 10-kilometer area will possess a plate of capacitor. So it will be a monster size capacitor. So we can't use unit as 1 farad. That is why we use 1 microfarad or 1 nanofarad. Okay, so farad is a big unit. Conventional configuration of the capacitors are two, series or parallel. You know this thing, the series capacitor is like this, the configuration of parallel capacitor is like this. And you have studied the series capacitor, the formula for the series capacitor. In the series capacitor, the voltage changes, but the charges on the plate always remains the same. So we have this V1 equals to Q over C1 for one capacitor, V2 equals to Q over C2 for second capacitor, and like that we can get VAB equals to this one. And when we dividing with Q, we are getting VAB or Q equals to 1 over C1 plus 1 over C2. Okay. So the equivalent capacitance, if we want to calculate, then this will be 1 over C equivalent equals to 1 over C1 plus 1 over C2. So this is the equivalent capacitor in the configuration of capacitors in series. Next, if we want to calculate the capacitance in parallel configuration, so in parallel configuration, the potential is used to be constant, and now the charge changes. There are two different charges on those two capacitors. So we can consider V1 equals to Q1 over C1 and V2 equals to Q2 over C2, and thus we are getting this formula Q equals to Q1 plus Q2, because the charge is different. So the total charge will be the sum of those two charges on those two plates, and thus we are getting C equivalent as capacitance, equivalent capacitance as C equals to C1 plus C2, and these two will be in C if the summation of all the capacitance we do, then only we can consider the equivalent capacitance. Okay, so let's do example. This is a configuration where three capacitors C1, C2 and C3 are connected. So, and we have to calculate the equivalent capacitance. So what we will do, first of all, we will calculate the equivalent capacitance for these two, because these two are in parallel configuration, and then we will consider this C3 also. So at last we can get these types of results. So C will be C3 C1 plus C2 over C1 plus C2 plus C3. Here is another example. There are three configurations. This is configuration A, this is configuration B, and this is your configuration C. Okay. So can you tell me which of these configurations has the lowest overall capacitance? We have two we have to find out which one has the lowest capacitance. Just calculate, tell me fast. You have 10 seconds. Calculate and tell me amongst these three configuration which have the lowest capacitance.
Configuration B.
B has the lowest capacitance. Okay,
Yes.
let's see. In configuration A, what we are getting? We are getting the net capacitance is C. B, the capacitance is C by 2. C, the capacitance is 2C. Yes. So the configuration B is correct. This is the next example.